We started the unit on circular motion and field forces by first talking about uniform circular motion in a good bit of detail, and then we moved on to talk about the gravitational force. Well, now we're going to focus on the last part of this unit, which is the other field force we're going to go into a bunch of detail on, which is specifically the electric force. So the electric force is a field force, meaning it's non-contact, or at least doesn't require contact, and it acts at a distance. Now, let's talk about field forces again for just a moment and remind ourselves how exactly they work with regard to the gravitational force, which was that a piece of matter with mass, so this fundamental property of mass, would generate a gravitational field. And this gravitational field applies gravitational forces to other pieces of matter that possess the same fundamental property of mass. So for instance, if we have like the Earth and the Moon here, those are not the scale, they apply gravitational forces to each other. Well, the electric force follows a very similar pattern with just some minor changes, which is that for the electric force, a piece of matter with charge, electric charge, generates an electric field. And this electric field applies electric forces to other pieces of matter with charge. So it only will happen between these charged pieces of matter. But what exactly is charge? It's been a while since we've talked about it. So we abbreviate charge with either a lowercase q or a capital Q, just like we abbreviate mass with a lowercase m or a capital M. And it's a fundamental property of matter that some pieces of matter may possess, not all pieces of matter do, that causes them to interact with other charged matter through these electric forces. Now, a few different things here. First off, where the gravitational force. Now, we've talked about a couple different types of mass, but when it came to the gravitational force, there was really only one type of interaction possible, which is that one gravitational mass attracts another gravitational mass, and they're pulled towards each other. And if we look at charged objects, we actually see that that's not the case here, that in some situations, they will be attracted to each other, but in other situations, they will actually repel. And this evidence is enough to tell us that there are actually two types of charge that exist that we need to think about. Now, what exactly are these two types? Well, we typically call them positive and negative. Now, this is an arbitrary name that was created by Benjamin Franklin in the late 1700s. He could have called it up and down, forward, backward, left, right, whatever. He went with positive and negative, and our convention has kept it that way ever since, but there's really no specific reason why one is one and the other is the other. Now, a couple of things here we'll notice, though, is looking over on this right-hand side, which is that when we have unlike charges, so if I have a positive and a negative, they're going to attract each other, much in the same way that the gravitational masses attract each other. But now we have a different situation. If we have two positives or two negative charges, so these are like charges, they're actually going to repel, and they're going to push each other away instead of pulling each other towards each other. A couple other things here for charge. The unit of charge is the Coulomb, which is abbreviated with a capital C, not a lowercase c, a capital C. Now, we'll find out that a Coulomb is a humongous amount of charge, and it's pretty infrequent that we deal with an entire Coulomb, particularly when we're doing all the static electricity type things we might be doing in a classroom. So frequently, we're actually going to see smaller versions of the Coulomb using metric prefixes. So for instance, we have little mc, which is the millicoulomb, which is times 10 to the minus 3. We have, now this is once again that Greek letter mu that we use for the coefficient of friction, but remember it's just a Greek letter, and that will stand for microcoulomb, which is times 10 to the minus 6. You might see a little nc, which is nanocoulomb, which is times 10 to the minus 9. And lastly, you might see little pc, which is picocoulomb, which is times 10 to the minus 12. Now, all of those are on your equation sheet on the back side, but it's good to be familiar with them at least. Now, charge has a unique property that we've not really dealt with in much detail in this course yet, which is that all charge is quantized. So this word quantized is going to be pretty new, into units of what is known as the elementary charge, which we abbreviate with a lowercase e. Okay, so what exactly does quantizing mean, and what does it say that something is quantized? Well, what that's telling us is, I want you to think about this like Lego blocks. If I look over here, if you have this little piece of Lego block, I'm going to label that 2e for the elementary charge. And I can have double of this, so 2e. I could have triple. I could have quadruple, as I do right here, which is 4e. And I can even start combining pieces together. So if I have 4e and 1e here, I could say, oh, this whole thing is 5e. But you notice, these are all in integer multiples of the elementary charge. 1e, 2e, 3e, 4e, 5, 6, 7, 8, 9, 10, etc. And what's important to note is that we don't have fractions. You don't have half a e. You don't have 2.7e. Because everything must be in these little pieces of what is known as the elementary charge. Now, specifically with quantizing, that means that the elementary charge is a quantum of charge. And if you have multiple, it would be quanta of charges. Okay, so a couple other things here. Well, first off, that something that makes this a little easier to understand is if we think about the smallest, let's actually start with the negative. The smallest negative charge we can possess, it would be an electron. And an electron, as far as we know, cannot be divisible into any other pieces. We can't cut in half an electron. We must always have whole pieces of electron. So the charge of an electron is actually equal to minus E, the elementary charge. Now similarly, the smallest positive charge that we can have, specifically the smallest isolated positive charge, is the charge of a proton, which is plus E, the elementary charge. We're never going to have anything broken down into pieces smaller than that. Now, the elementary charge, its actual value is 1.6 times 10 to the negative 19 coulombs, meaning that the charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. The charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. So, to make sure we fully understand, if we have one electron, okay, so like let's say we have an object, it has one extra electron, then it would have a charge, an overall charge of negative 1.6 times 10 to the negative 19 coulombs. What would be the next smallest negative charge it could have? Well, that would be 2 electrons. But that would be 2 times the elementary charge, which would be negative 3.2 times 10 to the negative 19 coulombs. The next one would be 3 electrons, so negative 4.8 times 10 to the negative 19 coulombs, etc. You're not going to have something in between, so we're not going to have 2. You're not going to have 0.4. You're not going to have 3.6. They're always going to be in these very set specific pieces. Additionally, as we mentioned a second ago, a coulomb is quite large, and specifically if an elementary charge is 1.6 times 10 to the negative 19 coulombs, if we inverse that, we get that 1 coulomb is 6.25 times 10 to the 18 electrons, which is literally trillions and trillions and trillions of electrons. You're hardly ever going to deal with that unless we're looking at bigger situations. Now, all macroscopic objects, anything that we deal with in our everyday life, is literally going to contain trillions and trillions of electric charges, with protons and with electrons, keeping in mind that neutrons are, of course, electrically neutral. So an object is charged if there is an imbalance of positive and negative charges. It's always going to have both, but if there is one that's more than the other, then we consider it to be charged. So, for instance, if we have a perfectly even amount of protons and electrons, well then we would say that is electrically neutral or not charged. Now realistically, this is actually not going to happen that often because there's always going to be a slight imbalance, but typically speaking, unless we have humongous imbalance, we're going to pretty much treat most objects as if they are electrically neutral. Now, if we have more protons, so if in other words, if we have lost electrons, well then we would say this is a positively charged object. So its charge would be positive. And if we have more electrons than protons, well then it would be negatively charged. And before we start talking about how charge can go from place to place, it's really important to consider this very, very key idea that there's something known as the law of conservation of charge, which is that the net charge of a closed system is constant. Okay, so constant meaning that it should not change. Now, what that is really telling me for most situations we're going to deal with is that typically charge is transferred or redistributed from one object to another or from one place to another. It's not created nor destroyed. Charges typically don't just pop into existence or disappear. They instead are moved from one place to another. So if I have these two spheres here, and this one has a lot of protons, now this is unrealistic, it should have some electrons, but this one has a really, really heavy amount of electrons, well what's going to happen is we're going to actually have something occur where the charges literally travel from one to the other and they're going to start balancing out. Now, couple things to keep in mind here, which is that typically it's going to be the negative charges that move. So specifically electrons, not protons. There's really two reasons for that. One, protons are stuck in the nucleus. They're much closer to the center of the atoms, whereas electrons are outside the nucleus in the electron cloud, the electron shells, so it's much easier for them to go to one atom to another. And additionally, protons are way, 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 way bigger. Although protons and electrons have the same charge, though of opposite sign, the mass of a proton is almost 2,000 times bigger that of an electron, meaning that it's going to be way, way harder to accelerate than an electron would be. Now, something to keep in mind here is that it actually is, now I want to say there's this word typically here, which might seem a little strange. It actually is possible to create charges or to destroy them, but they always happen in pairs. So, in other words, if I have some system with some set amount of charge and two pop into existence, well, I'm going to create a positive and a negative at the same time, so the net overall charge stays the same. And if two charges destroy themselves, and we're not going to go into the details of how this happens, it's always going to happen in a positive-negative pair, so once again, the overall net charge remains constant. Now, the last thing we want to talk about for this section, and really the last thing for the unit, is something that you should have learned in chemistry, but we're going to review, which is how do we quantify the force between electric charges. And we're going to use something that looks, one, really familiar from chemistry, but actually even looks really familiar from earlier in this unit, which is known as Coulomb's law, which was established in 1785 by a physicist named Coulomb, which is where the name comes from. And let's say I've got two charges, Q1, Q2, separated by some distance r, where technically r goes to the center of these two objects, but these charges are probably so tiny that it doesn't matter too much. So the electric force between these two charges, 1 and 2, in newtons, is equal to K, the absolute value of Q1 times Q2 over r squared. So let's point out a couple things here. First off, Q1 and Q2 are the charge on each charge in coulombs. So 1 coulomb, 2 coulomb, whatever. Now notice there are absolute value bars here. And so in other words, we should always be getting a positive number out of this equation. It's really just telling you the magnitude of the electric force. R is the separation distance between the two in meters. And K is Coulomb's constant, which K is 9 times 10 to the 9th newtons times meters squared per coulomb squared. This is just a proportionality constant, getting coulombs over meters squared, or coulomb squared over meter squared in terms of newtons. And it is on your equation sheet, but you probably want to write it down. We're going to see it pretty frequently, which is 9 times 10 to the 9th newtons times meters squared per coulomb squared. Couple of additional notes. One, this equation really only works for point charges. If I have, a plate of charges, that's going to be a different equation. The direction of the force depends on the type of charge. So for instance, if this was positive and negative, well then the direction would be towards each other. If instead this was positive and positive, the direction would be away from each other. So you have to look at that specifically. The equation really just gives you the magnitude. The direction you have to get specifically from are these positive, negative, or some combination of charges. And lastly, this is the electric force on each charge. It's a force pair. So charge 1 applies an electric force to charge 2. Charge 2 applies an electric force back to charge 1 in the opposite direction. So they should be the same amount. But one last thing I want to note here is that this equation, while from chemistry, also looks familiar because it looks a lot like Newton's law of universal gravitation, which was Fg is equal to G m1 m2 over r squared. These are both inverse square laws. They both involve products of particular properties of both objects. They both have a constant, K versus G. Very, very, very similar. So using this equation shouldn't be anything new. In fact, it's almost exactly identical to using that other one. So before we call it a day, let's just do a little practice problem. What is the electric force between two electrons that are separated by a distance of 1 picometer? All right, well, let's go ahead and identify our givens. So the charge of an electron is the negative elementary charge, so negative 1.6 times 10 to the negative 19 coulombs. That number is on your equation sheet, but you probably should write it down. You're going to see it a lot. R is 1 picometer, so 1 times 10 to the negative 12 meters. And I'm going to use Coulomb's law. Fe is equal to K, the absolute value of Q1 times Q2, over R squared. And we just really just need to plug in our numbers. We're going to put in 9 times 10 to the 9th newtons times meters squared per coulomb squared. The absolute value of negative 1.6 times 10 to the negative 19 coulombs and negative 1.6 times 10 to the negative 19 coulombs for each electron. And then over 1 times 10 to the negative 12. Notice this is squared. People forget the squared every time. And we get 2.304 times 10 to the negative 4 newtons. So specifically, because these are electrons, they're pushed away from each other, the electric force is 2.3 times 10 to the negative 4 newtons away from each other. Now this number may seem really, really tiny, and it is. It's a very small force. But you have to keep in mind that electrons are incredibly, incredibly, incredibly tiny objects. Their masses are times 10 to the negative 31 kilograms. So even though this seems like a small force, this is going to accelerate them incredibly, incredibly fast. Now, additionally, I want to really bring up another point, which is that we just talked about this equation here being similar to Coulomb's law. But one key difference we'll see is that for Coulomb's law, the constant K is 9 times 10 to the 9th, whereas for G, this constant was 6.67 times 10 to the minus 11. That is a humongous difference. That's times 10 to the 20 times difference. So the electric force is way, 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 way stronger than the gravitational force. Unbelievably stronger than the gravitational force. Evidence of that is if you ever do some of those like static electricity things we were doing in class where you rub two objects together and you're able to pick up some pieces of paper off the table. Well, keep in mind, that means nothing more than a handful of electrons is enough to create an electric force strong enough to overcome the entire gravitational force from the entire planet. It is a humongous difference in strength. So what are our main takeaways on this final lesson of the unit on electric forces? Well, one, can we evaluate the accuracy of scenarios by utilizing the quantized nature of charge? If we see some specific scenario, so if we're looking specifically at a tiny, tiny number of charges, we should always see charges that are in units of the elementary charge. If we have some fraction amount of that, we know that something must be wrong. Now, quick note on this, if you deal with anything that's like even picocoulombs, you have so many elementary charges there that we're always going to assume we've rounded to the nearest elementary charge, so this is really only talking about a handful of electrons. Can we apply the law of conservation of charge to analyze how charges are redistributed between objects? So if I touch two objects together, how do they move around? If I rub them together, how do they move around? Etc. And lastly, can we predict the electric force between charges using Coulomb's law? Fe is equal to k q1 q2 over r squared, those q's being in absolute values, and the types of charges involved. So if it's a positive and a negative, they attract. Positive and positive, they repel. Negative, negative, they repel. So that should be about it. This should conclude this unit on circular motion and field forces.